Hi, how are you all? In this video, I'm going to explain Newton's law of gravitation, which is going to be our lesson in 7.2 in the textbook. Here are the objectives of the lesson. The first objective, the students must know how to explain Newton's law of universal gravitation accounts for various phenomena including satellite, planetary orbits, falling objects, and the tides. Like, how is the satellite orbiting the Earth? Why doesn't it go away from the Earth? Why doesn't it fall down towards the Earth center? Also, planetary orbits, planets also, why they do not like uh, be attracted towards the stars, towards the sun like this. And then why are the tides? Okay. Second objective, students have to know how to apply Newton's law of universal gravitation to solve problems. There will be, I will add one more objective to know the effect of period and frequency. To say how long does the satellite take, to know how long does it take, the time, to know the frequency, the number of revolutions like this. Also, I am going to add these objectives. Okay, so let's go. And at the end of this video, we are going to come back to the objectives and see if we got them or not. So we are here in the book. Our lesson is going to be 7.2. You see Newton's law of universal gravitation. So these are the two objectives that we saw before a few minutes. So we are going to explain how Newton's law of universal gravitation accounts for various phenomena, including satellite, planetary orbits, falling objects, and the tides, and then to apply Newton's law of universal gravitation to solve the problem. What is the gravitational force? You know the story of Newton when he was sitting beside an apple tree and an apple hits his head. Okay, from that moment he start to study this phenomena. Why is this happening? And he concludes that there is a force of attraction between any two masses in the universe. This is going to be our gravitational force. So he said that any two masses in the universe, starting from atoms, molecules, up to stars, galaxies, planets, okay, they are attracting each other by equal forces. So like if we have two masses M1 and M2, they attract each other whatever the size of each mass. So for example, the Earth is attracting the moon is attracting the Earth. The Earth is 81, its size is 81 times that of the moon. But the force acting by the Earth on the moon is equal to the force acting by the moon on the Earth, like a tug of war. You know, two persons, the rope is balanced, for example, so as if the two people are attracting each other with the same force. So it is like action-reaction. It is related to Newton's third law. This force, we are going to call it gravitational force. The gravitational force that we know before, F of g is equal to mass times gravity. This is the origin of this equation. We will come back to our equation F of g equal mass times gravity after a few minutes. But here, this is the origin of the equation. So F of g depends on a constant number, capital G, which is a constant number. It is called the Newton's constant. It is about 6.67 times 10 power negative 11 Newton meter square over kilogram square. This number is constant, does not change. So the gravitational force is directly proportional to the masses, to the product of the masses, and inversely proportional to the square of the distance between the centers of these two masses. Okay, so if we say one of the masses is double, then the gravitational force will be double too. If the two masses are doubled at the same time, then times 2 times 2, so the gravitational force is going to be quadrupled, to be times 4. But if the distance between the two masses is doubled, then what will happen? The distance is doubled, yani times 2, but it has a square, so 2 squared, and it is in the denominator. So then, as if the force of gravity is divided by 2 squares, divided by 4, yani as if it will decrease by 4 times. M1, so it is the first mass in kilogram. M2, the second mass in kilogram, are the distance between the centers, and it is going to be in meters. So our book is using the symbol small r for the distance. Okay, other books are using, for example, D. Okay, F of G is our gravitational force, which is in Newton. The tides that happen, okay, is an evidence that there is a force of attraction between the Earth and the Moon. Okay, low tides and high tides are an evidence of attraction between the Earth and the Moon. Now here, let's come to our equation. Now, if we talk about a mass which is on the surface of the Earth, on the surface of a planet, then in this case, the planet, my students, is similar to the atom. Where is the mass of the atom? The massive part of the atom is at its center in the nucleus. Also, the mass of the planet is in its core. For example, the Earth, its core is about 90% of its mass. Okay, so we consider the mass of the planet, the mass of the star, the mass, even the mass of the galaxy to be the center of the planet or the center of the star. So this is why we say the distance between the mass of an object standing on the surface of the Earth is not zero. It is going to be the distance between that mass and the center of the Earth. So the distance is going to be the radius of the Earth, the radius of the planet. So here, the radius of the planet that I will consider it capital R is going to be the distance. Okay. So in this case, I will say f of g is equal to g m1 m2 over r square. Now the distance is the radius. F of g, we know it as mass times gravity, the mass of the object times the gravity. And here, so capital G, which is the constant number, times the mass of the planet times the mass of the object over r squared. So if I cancel mass with mass, I will end up with a new equation for the gravity, which is capital G, which is the constant number, which is 6.67 times 10 power negative 11 times the mass of the planet over the square of the radius of the planet. So by this equation, I can get the gravity of any planet if I know the mass and the radius of that planet. So M, capital M, considered to be the mass of the planet in kilogram. Capital R, considered to be the radius of the planet. Now G here can be called the gravitational field. So the mass is going to be gravitational mass. G here is in Newton per kilogram. When I use, for example, F of G equal mass times gravity. So then the gravity is F of G over mass, so Newton per kilogram. Or I may call it also free fall acceleration. The mass is considered here to be inertial mass. When we say F equal ma, I consider Newton's second law. So F equal ma, the only force acting is F of G equal ma. So A here is going to be meter per second square, which is also 9.8 is going to be about 9.8 for the Earth surface, for example. Let's do it for the Earth. The Earth gravity, so the mass of the Earth is about 5.98 times 10 to the 24 kilogram. Its radius is 6,380 kilometer. يعني 6.38 times 10 to the 6 meter. So let's do it. G is equal to capital G times the mass of the planet over the radius of the Earth square. So if I do this, I will get 9.799, so approximately 9.8 that we know. So it is 9.8, you can say Newton per kilogram, and also you can say 9.8 meter per second square. Here, one more thing. We know that if the object starts to be raised in air, so at a given height, as much as the object is going away from the Earth's surface, we know that its gravity will decrease until somewhere in space it become like weightless, يعني no more gravity. So in this case, as the distance increases away from the Earth, then here I can replace r by small r, which is the distance, and it is going to be the radius. So I have to get the distance from the satellite to the center of the Earth or the planet. So in this case, I have to add the radius plus the altitude, which is the height. Okay, so then r small is going to be the radius, r small, which is the distance, is going to be the radius plus the height, which is the altitude in meter. In this case, I am increasing this distance, I am increasing this number in the denominator, so then the gravity is going to decrease. We are going to do examples on this, but let me continue here. So here f of g is equal to f of c. Remember, احنا in the previous lesson, we talked about, or let me have an example first, and then I will come back to this point. Let me go to an example to practice this idea here. These two equations, okay? This one and this one. Okay, so let me go to the book. So here, why do objects falls? Objects fall because of the force of attraction, okay? The gravitational force that we talked about it, the gravitational force between the Earth center and the mass of the object. One may say, teacher, why can't we, is there a force of attraction between two chairs, between two tables, between two students? Yes, there is a force of attraction between them, as Newton said, but this force of attraction is very small. Why? Because of this constant, which is 6.67 times 10 power negative 11. Okay, it is going to be very small compared. Don't forget that if we are talking about two students, then we have to consider the Earth at the same time. So there is the force of attraction between the two students, and there is a force of attraction between every student and the Earth, which has a very, very big mass. So the force of attraction between the Earth and every student, which is going to be the weight of that student, will be too much larger than the force of attraction between the two students themselves. This is why we can't recognize the force of attraction between two students, but we can recognize it between very huge masses, like between planets, between stars. So I was talking about the tides. I said, the tides are low tides and high tides are the result of the attraction between the moon and the Earth. Why does the moon orbit the Earth? Because of the force of attraction. Why do planets orbit the sun? Because the sun is attracting these planets because of the gravitational force. In addition with the speed, I am going to talk about this point later after a few minutes. But here, let's practice our equation. For example, here, sample problem, find the distance between 0.3 kilogram billiard ball and 0.4 kilogram billiard ball. So we have two billiard balls, M1 and M2 are given. The force between them, you see, the gravitational force between them is 8.92 times 10 power negative 11 Newton. You see, very small force. This is why we can see that the two billiard balls are going close to each other, are attracting each other. Why? Because the force is very small compared to that of their weight. Now the question is to find the distance between them. So what we are going to do, put the equation f of g is equal capital G m1 m2 over r squared. So switch r squared and f of g. So then r squared is equal to capital G m1 m2 over f of g. I want to find r. So in this case, square root. So square root 6.67 times 10 power negative 11 times 0.3 times 0.4 over the force, which is 8.92 times 10 power negative 11. We are going to get 3 times 10 power negative 1 meter. So about 0.3 meter or 30 centimeter. So let's come to the practice. What must be the distance between two 0.8 kilogram? In this case, what I'm going to do is to do now f of g is g m1 m2 over r squared, but since m1 m2 are identical, I can say g m squared over r squared. Okay, the same question of the sample problem, the same force available. Okay, the constant still constant. We have changed the masses only. So again, we do the calculation, cross multiply, and then square root to get the distance, which is going to change a little. It is now 0.68 meter. Let's come to question 2. Mars has a mass of about, M1 is the mass of Mars, 6.4 times 10 to the 23 kilogram. There is a moon called Phobos orbiting Mars. It is 9.6 times 10 to the 15 kilograms, so M2. Again, the magnitude of the gravitational force between the two bodies is 4.6 times 10 to the 15 Newton. You see now, the force is remarkable now. It is clear. It is a very big force. Now, why? Because it is between a planet and its moon. How far apart are they? So in this case, we are going to do the equation once more. G m1 m2 over r squared. We have everything to the calculation. And here is the answer. It is going to be 9.44 times 10 to the 6 meter. You can do it yourself. Let's come to question 3. Find the magnitude of the gravitational force on a 66.5 kilogram person while standing on the surface of each of the following planets. We have Earth, Mars, Pluto, and in each case we are going to have the mass and the radius of each planet. What I am going to do, simply we can do f of g equal g m1, which is 66.5 times m2, which is that of the planet, over the radius of the planet squared. But what I am going to do in this equation is that to find the gravity of each planet. This way is better. And then, in order to practice the second equation, and then multiply, say f of g is equal to mass times gravity. We have the mass of the object, which is 66.5, multiply it by the gravity of each planet. So let's go. So for the Earth, I get g equal gm over r squared. We did it before a few minutes, and we got 9.79 meter per second squared. Now I say f of g mass times gravity, so I get 651 Newton. What was it? Mars and Pluto, the same thing. I do small g first. Okay, this equation, and then multiply it by the mass. So this is the gravity of Mars, which is about 1/3 that of the Earth. And here is the force of gravity. And here is the gravity of Pluto, which is very small compared to that of the Earth. And here the weight of the person on Pluto. Okay, so let's come back to the note. Here I will add this objective. I told you no before my new objective. Remember, in the previous lesson in uniform circular motion, we said that the centripetal force, which is the force that maintains the circular motion, can be the normal force on a roller coaster car, can be force of tension on a vine, for example, on a rope, on a pendulum. And also, we said it can be a friction on a car moving in a roundabout, for example. But also, we said it can be also the force of gravity. And this is going to be our new lesson, which is this lesson. So here, a satellite is orbiting the Earth, for example. The force of gravity is the force, is the centripetal force, is the force that maintains the circular motion. We know that the force of gravity is equal to mass times gravity, and we know that the centripetal force is mass times centripetal acceleration. Here, an evidence, okay, that gravity and acceleration are the same. We said this before. We said we can say it, we can call it gravitational field strength, or we can call it also free fall acceleration. So the centripetal acceleration and the gravitational field are going to be the same here for an object orbiting a given planet. The equation of G here, if I replace the equation of G, so it is going to be Newton's constant times the mass of the planet over the distance squared between the object and the center of the planet. And here we know that AC is equal to V squared over R. If I cancel R with square here, R with R, so I will end up with V squared equal G capital M over R. So V is going to be square root G, which is 6.67 times 10 power negative 11 times the mass of the planet over the distance between the object and the center of the planet. So if a satellite is orbiting the Earth at a given height, I can get the distance between the satellite and the center of the Earth, for example. If I know the mass of the Earth, so I can get the speed of the satellite. The new objective is to remind you something that we took last year about period and frequency. Remember, we took in grade 10 that period is the time required for one complete oscillation, and we took it also at the time required for one complete wave. Today, we are going to take it as the time required for one complete revolution, one complete rotation, one complete turn, one complete cycle. And the frequency, which is going to be small f, so from now on capital F for force, small f for frequency. So it is going to be the number of revolutions per second or per time. We said also in grade 10, if you remember, I am reminding you that the period and the frequency are inversely related. So I can say period equal 1 over frequency, and also I can say frequency equal 1 over period. The period is a time, so it is in second. Frequency is in hertz. Hertz means revolution per second, or simply RPS, rotation per second. Now, to relate this to our factors, which is the tangential speed, so you know the tangential speed is equal to distance over time. If I will consider the time to be the period, which is the time for one complete cycle, then the distance is going to be the circumference, the distance of one cycle, which is the circumference, which is going to be 2 pi r. So in this case, I can know the speed of the satellite, for example, if I know the distance from the satellite to the center of the planet, and if I know how much it takes to do one turn. Or if I know the speed, I can get how long can it do, it make for one turn. Now we said that the period is inversely related to the frequency, so this equation can be written also as V equal to pi r f, where f is the frequency. Remember, period was time for total time over number of turns. We are saying that the period is the time for one turn. So what if we have many turns, 20 turns? Then if I have the time of the 20 turns, divide the time over 20, I get the time for one turn. And also frequency is the inverse of period. So it can be n over t, number of turns per time. It is the number of revolutions per time, okay? So n considered to be number of revolutions, v the tangential speed in meter per second, and here t, small t, is going to be the time. Let's practice this. So we did the practice in page 232. Let me go to the section review in our book. So section review. Is going to be in your book, page 237, but in my book, it is 247. It is a different edition. Number one here, remember I told you that I will come back to the idea of gravitational force and the speed. Why is the satellite kept in its circular motion, kept in its orbit? Because of two factors, because of its speed and because of the gravitational force. The interaction between the speed and the force keep it in the track. So the speed will keep it from being fall towards the center of the earth, and the force of gravity keep it from going away in the space. Okay, so explain how the force due to gravity keeps the satellite in the orbit. The interaction between the force of gravity and the tangential speed will keep the satellite, will maintain the circular motion of the satellite. Is there a gravitational force between two students sitting in a classroom? We said between any two masses there is a force of attraction. Yes, so yes. If so, explain why you don't observe any effect of this force. We said because the force between the two students will be very much small compared to the force between every student and the mass of the Earth, which is the weight. And then let me go to question 4, and I will come back to question 3. Question 4, what is the magnitude of G, small g, يعني the gravitational field, at a height above Earth's surface where the free fall acceleration equal to 6.5 meter per second square? This is a trick question because we said that the gravitational field and the free fall acceleration are the same. So here G is going to be the same number, 6.5 meter per second square. So let's check the answers. So this is section review, page 237. So the answer of question 1, the interaction between tangential speed and gravitational force will maintain the circular motion of the satellite. We said the tangential speed will keep it from falling, the gravitational force will keep it from going away in space. And here in number 2, there is a force of attraction between two students, so yes. Why it is not recognized? Because the force will be very small. The masses are very small compared to the mass of the Earth, as we said. And finally here, how much is the gravity if AC is 6.5 meter per second square? We said F of G equal F of C. We cancel the mass and we get that they are equal. So then G is the same as the acceleration. Now if we come back to question 3, let me go to question 3. I will change it a little. So Earth has a mass of 5.97 times 10 to the 24 kilogram and a radius, while Saturn has a mass and radius also. Find the weight of 65 kilogram person at the following locations. Remember, we did for the Earth. So here, part A and B, I will skip part A and B. I will come to C and D for Saturn. So for Saturn, in order to get the force on the surface of Saturn, just I am going to do F of G equal G, capital G, which is 6.67 times 10 power negative 11, times the mass of the object, which is 65, times the mass of capital mass, the mass of the planet, which is 5.68 times 10 to the 26, over the radius, which is 6.03 times 10 to the 7 squared. Or I said, as I said before in the previous question, I prefer to do G, yani find the gravity first, G capital M over R square, and then multiply mass times gravity, and you will get the same answer. What do I want from this question is part D, and I will add more parts on it. So here now, what if the satellite is 1,000 kilometers above the surface of the Saturn? What if, sorry, the person, the astronaut, let's say, which is 65 kilogram, what if he is or she is 1,000 kilometers above the surface of Saturn? How can we get the gravity and then the force of the gravity? And then I will add some questions. So let's go. So Saturn has a mass of 5.68 times 10 to the 26 kilogram. The radius is given 6.03 times 10 to the 7 meter. Now here an object of 65 kilogram we said is found at a height of 1,000 kilometers from the surface. So this is part D. I made it part A and I added some other parts. Okay, my question here is find the acceleration of the object, and find the centripetal acceleration, which is the gravity. And then I ask a question in order to practice the other equation. So find the speed of the object at that altitude. Then how long does it take the object to make a half revolution? And then find the gravitational force that is available in the question itself. And finally, find the frequency. So let's go. So the first part. First of all, you have to get the distance. Don't forget this, it is very important. The distance is not the radius now. The distance is the radius plus the height, which is 1,000 kilometers. Yani 1 times 10 to the 6 meter. If I added them, I will get this number. So this is the new distance, 6.13 times 10 to the 7 meters. Then let me get A, which is G. It is capital G, capital M, the planet over the distance squared. We have everything, so I get about 10.1 meter per second squared, which is close to that of the Earth. Then to find the speed, I will use A equal V squared over R, or you can also use or here. Let me write here, or I can say V equal radical Gm over R. Remember this equation, okay? In both cases, I will get the same answer. So I will use this one. So A is 10.1 V squared over the distance, cross multiply. I will get 6.19 times 10 to the 8, but this is V squared, so square root. I will get V as to be 2.49 times 10 to the 4 meter per second. Now part C, for half revolution, how can you get, how long does it take? So first let me get the period, 2 pi r over V. I have everything. I get 1.55 times 10 to the 4 second. This is the period. But I want the time for half revolution. So remember we said period is equal to time over number of revolutions. And here we got the period, which is 1.55 times 10 to the 4 equal the time over half revolution, which is 0.5. Cross multiply, I will get this number. Now here, part D of the question, it was find the force of gravity. So I can use G m1 m2 over r square, or simply mg. I get G small g, so I can use mg. M is 65 kilogram. G, I get it at that height, 10.1. So I will get 655 Newton. To find the frequency, the last part, don't forget the frequency is 1 over the period. If or you can use n over small t. Remember, we said the frequency is n over small t. If you use n over small t, then it is going to be 0.5 over the answer here. Or if I use the relation between frequency and period, it will be 1 over the period, which is this much. In this case, in both cases, I can get 6.45 times 10 negative 5 hertz. Okay, so let's come back now to the objectives. So coming back to the objectives now. So now we know why planets orbit the sun, why are the moons for many planets are orbiting their planets, why is our moon orbiting the Earth, why is the satellites, many satellites are orbiting the Earth. Okay, why are the tides, low tides and high tides happening? All of this are due to the attraction between masses, the Newton's gravitational law of attraction. And also we knew how to apply Newton's law of universal gravitation, which is related to the directly proportional to the masses and inversely proportional to the square of the distance. And it was G m1 m2 over r squared. And also from that equation, we get the equation of the gravity for a planet and the gravity of the planet at a given height. So we can get the distance. Also, we said that the gravity and the acceleration are the same, so we can play with the equations of last lesson and this lesson, the uniform circular motion equations and this lesson. And so we get equations about period, frequency, etc. And we knew how to deal with these equations and with the questions on them. I hope you got these objectives. Thank you very much. Okay, see you next lesson. Bye.